quartic theory. So let me just remind you what we did. I won't write down all the values and so on, but I'll just write down the value of the fixed point. Oh, don't have it here. Quartic. I won't write all the. And the fixed points were and we had a recursion relation. I'll just write that down. So first point we made was, I think maybe I should have made it, that if this correction term is 0, so you're in the limit that u goes to 0, r equals 0, u equals 0 is a fixed point. That's the Gaussian fixed point. And if you change r a little bit from 0, you can see that r prime gets bigger. In fact, this one also, when epsilon is greater than 0, this also gets bigger. So you start at the fixed point where both are 0, and then if you perturb it, you go away from that. Both of them get bigger. This fixed point is a little different because we calculated the eigenvalues. And if I have the eigenvalues for the perturbation were 4 minus So indeed, this eigenvalue continues to be much greater than 1. In fact, it's close to 4. But this one is a little less than 1. Okay, actually I should say it's just I put an approximate because it's less than 1 only to the extent of this epsilon being non-zero. Okay. So in other words, and I also told you that this power, the fact that it's 2 squared is due to the dimension of the coupling constant. The fact that this is like a mass squared, momentum squared, that's why it goes to 4. And the fact that this starts off as 1 is the fact that naively this has 0 dimension. It's a dimensionless object. But this changes that and makes it a little less than 1, which is different from the behavior here. Okay, it actually goes. Later on, we'll see that these distinctions are important. How many eigenvalues are greater than 1? How many are less than 1? And these are basically, this eigenvalue has a word, it's called a relevant coupling. This, I will call it marginal or marginally irrelevant. In the sense, marginally because it's when epsilon is small, it's a small deviation. Okay? Later on, I'll also talk about couplings which, let's say, call it W, which have the property that W prime is, let's say, 1/4 of W plus corrections. So this is 1/4 without any interactions, just by dimensional reasons, and these will be called irrelevant couplings. Okay? So this is just looking ahead because we're going to do that. So now we're studying the behavior near this fixed point, and I wrote down a matrix. So I won't write down the matrix, but I'll just write down the net result of the perturbation. So we wrote down a matrix like this in terms of this bracket notation, lambda 1 and in this form you can easily see that if I raise this to the nth power, all that happens is this gets multiplied by n. It's easy to see. And then I wrote down a recursion relation, which I'll write it down now, R L plus n. So this is the so this matrix tells you how the deviations from the fixed point change with iteration. So I'll write down, so r and u are the variables. So r L plus n minus the fixed point is lambda 1 to the power of n. So let me write down this expression. We define these things. Plus, I'll write out the lambda 2 term also, plus lambda 2 to the power of n. And similarly, u L plus n minus u star is the same lambda 1 to the power of n, except this changes, it's w12 v11. And here it's lambda 2 to the power of n. W22 plus W22 V22. So that's the behavior. Okay. And then I drew this figure. So, so the first approximation we can neglect this term because this lambda 2 is much less than lambda 1, and you see that this thing is going to grow as you iterate. So if you want this to go to the fixed point, near the fixed point, then you have to tune things so that this linear combination is 0. So let me factor out an omega 1 w11 and write this like this. And here I can factor out a w12 and write it like that. Okay. So this same combination occurs here and here. So if you choose your couplings, this linear combination to equal 0, then that's the necessary condition for the deviation not to grow, okay, as you iterate. Okay. So suppose you tune this to 0, so that this term is 0, then what you're left with is this term, and in this term lambda 2 is less than 1. Okay. So this one gets smaller and smaller and smaller. Is this clear? So this tuning of the coupling is basically a choice of your parameters in the Hamiltonian, and one of the physical quantities that go in deciding those parameters is the temperature of that, describing that theory. So we'll call that parameter temperature, and we'll say we'll choose the temperature so that this linear combination is 0, and that temperature will be called Tc. So at T equals Tc, this combination is 0. Okay. And then you're left with this, but this one keeps decreasing with each iteration. So that gave us this figure. Oh, I think I had U here and R there. Where is the figure? Let me use the same. Yes. So this is a linear relation between R and U. So R L and U L, or R naught and U naught if L is 0. So you choose for any given R naught, there is some U naught which makes it 0, or for any given U naught, there is some R naught which makes it 0. So there's a set of points which I've drawn as a line. We'll call this point, I think I call it, this is a fixed point. So this is the fixed point. So for any U, there's some R that makes that 0. So this is that point. So for instance, if your starting Hamiltonian had a U naught, and you chose R naught to lie there, then you could call that, this point, you can call it the critical point. For instance, this notation. So generically, as you change the, so this line corresponds to T equals Tc. So you've chosen it to lie along this line, that's this condition being 0. And we've seen that as you iterate, it it gets smaller with each iteration, so it flows like that. Okay? If you choose now, so generically you can start your theory with a series of couplings parameterized by this parameter which you call temperature, such that at t equals Tc you get, let's say, to this point. So this is my point R0C, U0C starting. As you change t, you will get different points. So you'll get a different set of starting points depending on the t, and the generic behavior is going to be that if this t minus Tc is small enough, if this number is very small, so you're close, then this will also iterate and go near the fixed point. So they'll all go like that until, so that's governed by this term because it's getting smaller, until, because this is not exactly 0, this thing becomes big. So this thing starts to dominate over that, and then it starts growing. Okay? So then it will go off. Go off like that. Okay? And then you can ask, how does this curve, how do these curves look as you approach the critical point, but you're not exactly on it, and they'll approach some asymptotic line like that. So the shape of this line depends on the details, but I'm just drawing it here. Okay? So this curve, so this is, let's say, I think this curve, I've called it the name D. This is Wilson's notation. So this is a unique trajectory to which all these guys asymptote. Okay, and it starts from this fixed point and goes off like that. So this is called the renormalized trajectory. And this will have significance later on. Of course, where do these things go finally? We don't know. It could go to a fixed point where some other fixed point, or it could go to some trivial fixed point where the correlation length is 0. So remember here, t equals Tc, the correlation length is infinite.
The linearized analysis will only tell you the neighborhood.
Yes. So this is the neighborhood. Yeah, so where it goes there we don't know. So now why is C infinite? I defined t equals Tc as being C is infinite, but now I've also defined it as this line given by that equation. But the reason it's infinite is very simple, because all these points are on one trajectory and they all have the same correlation length, the physical correlation length. This one clearly has correlation length infinite, that's a fixed point. Remember, the fixed point always has infinite. Why? Because C prime always has to be half of C with each iteration. But if it's a fixed point, then C prime must be equal to C. Why? Because the expression, it's mathematically the Hamiltonian hasn't changed, so you plug in the parameters, the value you get for the correlation length has to come out the same as a number. So as a number, this has to equal that at the fixed point, but you know that this also has to equal that on dimensional grounds. So the only possibility is C is infinite, or 0, which we are excluding. So this guy definitely has C is infinite, so all these guys have C equals infinite. So they're all so in fact, that's why it's called the critical surface. So this is the critical surface. So typically, at a second order phase transition, you tune a temperature and you'll be on this critical surface. But not necessarily at that fixed point. You could be anywhere. Okay, so now what I want to do next is to use this picture to get the expression for the way the critical, the way the correlation length diverges as t minus Tc. So remember, there is an exponent C goes as 1 by t minus Tc to some power, which we call nu. We know it blows up, but to what power? So the question is, can you fix this nu? And in mean field theory and the Gaussian model, we got nu is half. Okay, so here we hope to get something different. So yeah.
On this critical surface,
Yes.
let's start with some theory, U naught R naught.
Yes.
Away from the critical point.
Yeah.
It will still take infinitely many iterations to get to that point.
To get to the fixed point. Yes.
And in principle, I could have started with a theory which is defined by U naught R naught on the renormalized trajectory.
Yes. You could start here, right?
That would flow.
That would flow to some, yes, yes. Yeah, actually, yes. Right, in fact, I'll come to that point when we talk about the behavior of correlation lengths in this region, okay? So as Nemanja was pointing out, one interesting thing is this is a little deceptive because I've drawn this as very big and this is just one point, but actually the theory spends a lot of time in this region, okay? Why? Because it's a logarithmic scale. So you go from, let's say, 1 to 0.1 in a certain amount of time, then you go from 0.1 to 0.01 in the same amount of time, and you keep going like that till you hit 0, which takes an infinite number of iterations if you're right at the critical point. So actually you spend a lot of time in this region. If you think of the particle moving, you really spend a lot of time in this region, and that's one of the reasons why this behavior is so important. That dominates your behavior after a few iterations. You spend a lot of time in this region. So you can calculate a lot of things just substituting this Hamiltonian for your actual Hamiltonian.
You have to draw a mechanical potential.
Yeah, you could do that, yeah. Right.
Which would have mimicked this to be the phase-space trajectory.
Yeah, so
That would be like some shoulder and
that's right, yeah.
big potential.
Yeah, so the precise shape of the potential will depend on how many stable and fixed points are on, but that analogy is good because we'll do that later on when we talk about the topology of when you have various fixed points. But roughly speaking, I can just say, since this question was asked, if you have a potential like that, if you start this with just enough velocity to reach there, then the particle goes and stops there. But to actually reach that point, it takes an infinite amount of time. You can just do it in classical mechanics. And if you're a little bit off from that, then you have to think of this as a hill and projecting in this direction, and then you're off. You go off maybe on the side, and then you roll off somewhere else. So you can make analogies like that about how the thing flows, and we'll do that later on. But this is the simplest behavior that we can have for where there's just one direction. So this is one direction where the eigenvalue grows, and the other direction it's shrinking. Okay, so how do you calculate this xi? So the first point is to write this equation near t equals tc. Okay, since at t equals tc this is 0, and we know everything is analytic as far as the Hamiltonian is concerned, this must be away from the fixed point, this must be away from the critical point, this must be proportional to t minus tc. Okay, so I can write, and I'm neglecting this now. So I can write, because this is the guy that determines the correlation length, the relevant. This is the analog of the R in your Gaussian theory. Okay, this one. Remember, R equals 0 was the point where xi was infinite, and you got xi is something like 1 over root R, and that's how you got the power of half. Okay? So we're doing the analog of that here. So we can write this thing as some function of t minus tc, some constant times t minus tc near the critical point. So this equation looks like so let me write it like this. Where is it? So you get R L plus n minus R star is lambda 1 to the power of n, some number times t minus tc. So this L just says you're starting from RL. If you start from R naught, you can just put R naught, that doesn't matter. And UL plus n minus U star is lambda 1 n W12 . Actually, in our example, if you look at the matrix, this one is actually 0. If you remember, the W was 1 and 0. So for this particular example, this coefficient turns out to be 0. But in general, of course, it's not 0. So we are interested in the behavior of this one. So one thing you can see, okay, so let's say as I said, C is given by some analytic formula which I've been calling X as a function of, what did I call it? R and U. So I give a R and U to you, that fixes your Hamiltonian. Then I can calculate C. Okay. Now R and U are going to be parameterized by this T. So we will write, so I will write this as, so let me write this equation. X of R L plus N, U L plus N is 2 to the power of minus L minus N, X R naught U naught. Do you see why that is true? This is just saying that starting from R naught, I've done L plus N blockings. So in the units of my new lattice spacing, the correlation length is down by a factor of that, because this is the expression for the correlation length. Yeah. No, why? This one? If it's 0, it will be just 0.
Yeah,
That's all.
because we are finding the critical point by putting that equal to 0.
This part.
Yeah. But if that term vanishes, then how do you get that?
No, this term is 0. So we still have to put this to 0. This is the same as this, right?
Yeah,
This one is not 0. Oh, both of them are 0. It's a trivial theory. Nothing's happening. Yeah. So we're setting this to 0 because that governs how this blows up. So I'm going to write. I'm going to write another equation which you can look at that and tell me if you agree with it. R L plus N plus 1 at T minus R star for T minus Tc equals tau by lambda 1 is the same as R L plus Nt minus R star for T minus Tc equals tau. Can you see that? You see what I've done? I've increased the iterations by 1, which normally would make your C smaller by a factor of half. But I shouldn't say, normally would bring an extra factor of lambda 1, multiplying it, because this n has become n plus 1. So you get one more lambda compared to this. But on the other hand, I've reduced this by lambda. So I've divided this by lambda. Okay? So this lambda, so you start closer to the critical point by a factor lambda and iterate once more. That's equivalent to starting at this point and iterating one less time. Is this clear? All I'm saying is, if I write this, okay, so let's write R n plus 1 here. This is lambda n plus 1, right? So I've got an extra factor of lambda. But suppose I start at a temperature closer to the critical point. Then this lambda will cancel that 1. So I get back the same formula. So that's what this statement is saying. So the extra step can be compensated by going closer to the critical temperature. Okay? So you get the relation that C of Tc, so let's call this number tau by lambda, is equal to times 2 to the power of minus L minus N minus 1 equal C tau C plus tau 2 to the power of minus L minus N. Okay? So one extra iteration, start closer, they're equal. Once you got this idea, you're home, because you can now assume a form for C. So let's assume that this C goes as tau to the power of minus nu. So tau is T minus Tc. Okay. So you get this is tau by lambda. So because the deviation is tau by lambda, here I have to put tau by lambda to the power of minus nu times 2 to the power of minus L minus n. Here is tau minus nu times okay. So everything cancels, and you can see that lambda 1 to the power of nu has to be equal to 2. Cancel all the taus, all the powers of 2, and you're left with this relation. So one factor of lambda has to give that extra factor of 2. So it has to be raised to some power clearly, okay, because lambda 1 is not equal to 2. So what is that power? So nu is log 2 by log lambda. This is actually the same formula we got in the Gaussian case also when we studied Kadanoff blocking. And there lambda was 4, so you got 1 by 2. Okay, so in the Gaussian case, lambda was equal to 4. So nu was half. Here you have to put your value of lambda for the fixed point, which is this. Okay, and you'll get log 2. So you expand that, of course, to linear order and epsilon, because this is all valid only. You'll get that. Log lambda linear order is that. So the log 2's cancel, and this becomes half plus 1 by 12 epsilon plus order epsilon squared. So what is this? This is nu. Okay. So this is the Gaussian value. This is the deviation. So is this calculation clear? We're just seeing. So the crucial idea here is that as you go closer to the critical point by a factor lambda, t minus cc, you have to do one more iteration. So it changes things, the correlation length by a factor of 2. So the lambda to the power of that, whatever power, has to compensate for that 2. So that's the power. So this is a simple calculation, but it demonstrates many things. First of all, where did this log 2 come from? The log 2 came because you're blocking in units of 2, I mean 2 spins at a time. So that has cancelled out. Here there's no log 2. So that means you could have done this blocking in steps of 3, I mean 3 spins at a time or 4, it wouldn't have mattered, you'd get the same answer. So that's what you would call in general scheme independence. By scheme you mean the when you do an RG transformation, there are some conventions you have to use, which the details of the transformation you do. The final physical result should not depend on that. If it did, then there's something wrong. So that's the scheme independence. The second point, second point is, of course, it differs from mean field. And the third, probably the most interesting point, is that it doesn't have any reference to what was u naught, what your starting point was. No reference to u naught or r naught. Well, you had to be on the critical trajectory, but you could have started with any u naught. I mean, you have to be close. There's a close to the critical trajectory, but any u naught. This answer just depends on epsilon, the dimension you're in. So this is the famous property of universality. So the critical exponent does not depend on the details of your starting Hamiltonian, which here is what we call u naught and r naught. Okay, that's something which was experimentally known, but this RG proves it for you. Well, proves in the sense in this approximation. Okay. So I don't want to use the word prove. This is what is called the famous epsilon expansion. You may have heard that. This is in this parameter epsilon. And what we've done is just linear leading order in epsilon we found in an answer. In general, there will be a series epsilon, and you don't even expect in general that it will converge. It will be in some asymptotic series typically, and then you might have to do some techniques, like Borel summation, all kinds of numerical things. But in a quantitative way, it demonstrates many of the properties that you expect, and the series actually converges. I mean, numerically, it gives you good answers, this epsilon expansion. Okay. So that concludes our first run of the fixed point behavior and the RG analysis of this theory. Any questions about this? It's a good place to ask. Because what I want to do next is to see how much, this is a simplified version of the full RG, and we have to analyze a little bit the consistency of this approximation. And I want to introduce the idea of the irrelevant perturbations. Remember, irrelevant perturbations are things which, I think I wrote it down, yeah, things like this. Why are we interested in this? Because it will turn out there are an infinite number of them. Okay. Here there was just 2 coupling constants. There are an infinite number of coupling constants in this theory like this. And we need to show that they don't affect this calculation. Okay. So I'm going to show you what I mean by these infinite number of couplings and a little bit of keeping track of powers of epsilon to show that this analysis is not affected by those irrelevant couplings. So that's what I'm going to do. So if there are any questions, you should stop and ask. Epsilon is supposed to be small, but eventually they use it for epsilon equals 1 because it turns out that I think the numbers, the denominator are things like there's some 54 and things like that. So it actually numerically it's a good approximation even with epsilon equals 1. And it seems to agree with numerical calculations.
Can one see any difference in 3D, 2D system?
Oh, 2D you want to take epsilon to 2. That I don't think people have tried.
There are many systems in 2D.
Right. Yes, 2D of course you have more powerful techniques. You don't need to use RG for that. Yeah. I should mention that people have studied epsilon expansions for this sigma 6th model. So this is D minus 4. They've studied D minus 3 or 3 minus D, whatever, and found fixed points.
Say 5 to the power 6.
Yes.
Then in some cases you don't have critical points.
Well, in the okay, I don't know the full literature, but I know that in the large N, they've studied fixed point has been shown for D equals 3.
There also.
Yeah, same kind of analysis. But that analysis is reliable only in the large N. So for the rest of the students, I'll say that this is just one spin, but you could have N spins, I going from 1 to N. So N feels like this, and you can study how you can do this analysis for that situation. And if this I goes from 1 to N, you have to do the combinatorics. And it turns out that when N is approaching infinity, a lot of things simplify. So people do what is called a 1 over N expansion, and they study properties. Okay. But I won't do that for this. So what I want to do now is to study this model without any I, but the role, how these things come in, because that's very important for the exact. So as I said, this is an approximate RG, but I've kept only 2 parameters, so we'll do the exact one. I won't do the exact one, but I'll show you what is involved in the irrelevant variables. So I'm going to erase this. Yeah, so I'll just start afresh, that's the best. And then the other thing I want to do is to understand how correlation lengths behave in the low energy limit. So as I said, in the low energy limit, you're dominated by this region. So you can make fairly strong statements about how correlation lengths behave in general. So I shouldn't have erased that anyway. This I shouldn't have erased. Half Q squared plus R. So So this is 4 sigmas. I won't write it out. And yes, so now the question is, yeah, so as I said, our motivation is to understand things that do that. Okay, so remember r prime is 4r plus, oh, I should write that out. Okay, 4r plus 3cu by 1 plus r, and u prime is 2 to the power of epsilon u minus 9cu squared by 1 plus r squared. So what happens when you have terms like this? So where do we get terms like this? Well, first of all, so actually what you should do is look at the nature of the diagrams. So if you remember that at the fixed point, this guy is of order epsilon. U is of order epsilon. This term is of order epsilon squared. This term is of order epsilon. So the question is, when you add this coupling into your recursion relation, how is it going to affect these terms? Okay. So to leading order in U, the only diagram, so we do perturbation. The leading order in U, there's only one diagram, which is this one. Remember, sigma 1, sigma naught, sigma naught, sigma 1 with a U.
What is W?
Oh, W is some other coupling which I'm going to introduce in the model. As I said, the model actually has an infinite number of couplings. We've just picked 2 of them, and I'm going to show you in a minute what the W will be. But here I just want to say, suppose there is some W which has some behavior like this. How is it going to affect these equations? Okay. So I want to show you that in first order in U, there's nothing that can happen. There's just this diagram, and if you want the tree diagram where this is sigma naught, sigma naught, sigma naught, sigma naught. Okay. So how can this appear in your equation? So you write an equation of the form. So let's write down a recursion relation for W. So first I want to determine what form of this W could be, what order in epsilon it could be, and then see if it affects the equation. Okay. So W has to come from diagrams of this theory. To leading order, these are the only diagrams. Okay, and this is contributing, already we know it's contributing to R, doesn't introduce any new interactions. This is the old interaction U. So to leading order in U, linear order in U, you don't get any contribution to any coupling W that you can have in the theory. So W would be some coupling involving sigmas and some other combination. Okay, I've not even specified what it is, but clearly to leading order, these are the only things, so there's nothing else. So that means this has to be at least order epsilon squared. It has to come at order U squared. Okay, order epsilon squared, or it could. So I should write it as. So yeah, I should say U squared. U, since U is of order epsilon, this is of order epsilon squared. So you can have things like U squared, or in principle you can have U times W, W squared, etc. So I'm trying to see what are the nonlinear terms that would come on this side for a hypothetical coupling W prime. So all I'm saying right now is it has to start off as U squared. So it's of order epsilon squared at least. So all these terms are necessarily higher order. Okay. So to order epsilon there's no change. It can at best be of order epsilon squared. Okay. Now you can see, suppose W prime has a fixed point value of order epsilon squared. Will it affect these equations? Okay. So suppose W fixed point is order epsilon squared, which seems to be the case. It could be higher, but at least which of these equations can it spoil? Well, in this equation is of order epsilon. The leading correction is order epsilon. So if I add an order epsilon squared, that's a higher order correction. So it's not going to affect the leading order analysis here. But this term is order epsilon squared. So if this occurs in a linear way in this equation as a U prime, then it will affect this leading behavior. Okay? So the conclusion is, if W star, if it's of order epsilon squared, you show that, and you show that it doesn't occur in this at linear order, you're okay. Okay. So what we have to do is to show that A, W star is at least order epsilon squared, and B, it doesn't occur here at order epsilon squared, but only in higher order quadratic, say epsilon fourth or something. If you show those two things, then you argue that these variables will not upset this analysis. Okay. So this is an example of the kind of analysis that you have to do. Yeah, I'm just good. Yeah, right. That's just what I'm going to do now. So I should point out first of all that so let me start by writing down a general object here, more general object, and I'll give you what I mean. So I will not write it like that. I'll just say there is some function u2 of q times sigma q, sigma minus q. So here u2 of q is just q squared plus r. Okay? But we will see later on that after a few iterations, it won't be just the quadratic in sigma term in your Hamiltonian won't be just like that. It will be much more complicated. Similarly, the quartic term, here it's just one constant times 4 spins. But in general, it won't be like that. You'll have, so I'll write it now, q1, q2, q3, q4. In general, it will be like this. With a delta function.
Effectively some higher variance.
Here it's just higher. Yeah, actually you should go on and there'll be more terms. So you can go from q1 to q6, and you can write, so this I'll call u4, u6, q1 to q6, sigma q1 to sigma q6, delta function q1, and so on. Okay. This is the most general Hamiltonian you can write down. And if you do our analysis to this Hamiltonian, integrate, do a recursion a few times, you're definitely going to end up with things like this. In fact, I already showed you that we had a diagram like this, which we neglected. So this was sigma naught, sigma naught, sigma naught, sigma naught, sigma naught, sigma naught. This is sigma 1. So when we contracted this propagated the high energy field out, we got a term with 6 sigma naughts. So that's a term that comes here. Similarly, there'll be corrections to this. We've already calculated that. We had a diagram like this.
You at least have to assume that which is locally doesn't have impact.
It will be analytic. But it can have a power series to arbitrary order, but it will have a power series about q equals 0. In fact, I'll use that in a minute. Yeah, I'll come to that point. So this is your q1, q2, q3, q4, sigma naught, sigma naught, sigma naught, sigma naught. So these are the high energy propagators. So this is, let's say, so let me q1, q2. So let's say this is P. Then this guy is minus q1 minus q2 minus P. So it's q1 plus q2 plus P going that way. But since by convention I'm putting them all in here, I've written it like this. Doesn't matter, you can put it either way. And then q3 and q4 are this. Now if you actually calculate this thing, it's not just going to be, this graph is going to be a function of q1, q2, q3, q4. Okay? When we calculated the correction to this, we set all these guys to 0. And we said the leading term is just a constant, 0 momentum. That's the correction to this. That was what gave this guy. Okay, this is u times u. But in general, it's going to give you something that has all the momenta in it. You're going to get something like this. Okay. So now the question is, what do you do when you have such? So let me just write down some expressions for this thing. Okay, so what is the, so how are your, by the way, so this action is what people nowadays call the Wilson action. I'm using the word Hamiltonian and action interchangeably. When you do field theory, you write down an action and a Euclidean version of that. That same object in statistical mechanics or condensed matter physics is typically the Hamiltonian of that theory. So it's just it's called the Wilson action to be distinguished from your original Bayer action. So this would be what you call the Bayer action. So your Bayer action typically is a very simple action which you choose, and as you iterate the RG operation, you get a more complicated thing, and at any point after L iterations you get something, and that's called the Wilson action. So this has a, and in the way we're doing it, the cutoff is always there, and we're using everything in terms of the cutoff, which is of 1, which set the cutoff to 1.
The number of iterations is effectively that.
Well, okay. So if your initial cutoff is L, the new cutoff will be 2 to the power of L, L naught. So it's, but you will be working in units where that is 1, so all your momenta will be divided by that factor. But in these integrals, you'll always write it so that it's, this is 0 to 1. You always rescale so it's 0 to 1. So let's write down the exact RG expression to which these guys are a simplified form. So here you will recognize the various pieces, U2 prime Q. So the leading term is the famous rescaling factor. This came from a rescaling times U2 . Okay. Do you remember this? Remember we said the new variables we are going to use in here are Q prime, which will be 2Q. Okay. So after the iteration, your variable is Q prime. So your original momentum is Q prime by 2. So after the iteration, I'm using, so you can call this Q prime if you want, but I call it, so this is actually Q prime, and all the variables that go in here are the variables of the original Hamiltonian, so a Q prime by 2. So if you want, you can put a Q prime and make it Q prime by 2. Okay. So this is your rescaled momentum. So this again goes from 0 to 1. So I'm going to drop the primes, I'll keep writing primes otherwise. So this was your first term. Plus, so remember, if you remember, we got Q squared by 4 plus R in the Gaussian model. This is just Q squared by 4 by R. Then we rescaled by a factor 4. We chose this to be 4 and got rid of this 4, and that became 4R. So R prime was 4R. That was the rescaling. So that factor still sits here. But now it has to worry about all these guys. So the first term is this one. That's all I'm going to write. So what is this now? More generally, this is U4. So what are the momenta that go in here? So in my units, this is Q by 2, Q by 2. So original, let me call it Q prime by 2, Q prime. So the original momentum was Q. In the new variables, it's Q prime by 2, and this is some P. Okay. So that's why I'm calling it Q prime by 2, Q prime by 2. So in the new variables, it's Q prime by 2. So it's U4, and so this vertex now has to be labeled by the momenta. So what is this vertex? So what is the vertex that goes in here? So there's Q by 2 here, Q by 2 coming out that way, so we put minus Q by 2 here, going in like that. Then there's a momentum P like that, and minus P like that. It's this vertex that is being used in this diagram. Okay? So the momentum dependence is like that. So if your U4 has momentum dependence, you have to specify all these momenta, which we were not doing before. We just assumed it's a constant. But actually you have to put all that. So it's Q by 2 minus Q by 2, P minus P, by, now the propagator is no longer Q squared plus R, it's this whole thing. That's the propagator. It's a Gaussian integral. by u, and the momentum variable is p, so it's u2 of p. And this has to be integrated half less than p less than 1. So that's the first correction. Okay, plus higher orders. Okay. So this is actually, now I'm going to write the equation for u4 also, and then we'll. So u4, we have this diagram. So I'll just write the answer and you can easily recognize it. So u4, q1, q2, q3, q4. And remember now we are 4 spins. So we had 4 of these, to the power of 4. And there were 3 delta functions. It was like that. And then the tree level term, which is u4, all momenta halved. That's the same rescaling. Plus the correction. And we estimated the correction, it was like this. So this is this diagram. So what's the momenta that goes into this vertex? It's q1, q2, p, and this one. Okay. So it's q1 by 2, q2 by 2, p minus q1 by 2 minus q2 by 2 minus p times this vertex. What's the momenta that goes here? It's q3, q4, p, this. Okay. And of course, in the rescale variable, it's q3 by 2, q4 by 2, and so on. So it's u4 times q3 by 2, q4 by 2 minus p minus q3 by 2 minus q4 by 2 plus p. And the denominator, there are 2 propagators now, u2p, u2. The other momentum is q1 by 2 plus q2 by 2 plus p. Higher order. And I won't even write down the equation for u6. So this is u4 prime. This is u2 prime. And then there'll be u6 prime of which will have this diagram. Okay, so this will be some product of u. Oh, this is the propagator. In this diagram, remember when we did this previously, we had 1 over q squared plus r. This is also 1 over, but here now we're not calling it q squared plus r, that whole thing is just this. So 1 over u2 is the propagator. So we're doing Gaussian integrals with this as your the exponent, so that comes out as propagators. So actually, these are the equations that the RG gives you, not the simple ones that we wrote down. So these are an enormous number of, it's an equation for functions. Okay, they're all functions. So it's a functional equation. And when we wrote this infinite number of functional equations involving functions, we reduced it to 2 algebraic equations. So it's an enormous simplification that has happened. So if you really want to justify that, you have to argue that these other terms don't affect your critical behavior and the fixed point behavior. Okay. It's not very hard actually. So I'll just do the I'll do it for the u2, and I'll leave the u4. You can read it in Wilson's article. So so here I have to tell you something. So as I said, Nemani was asking. So these things, the Wilson action is basically analytic in the momenta. Okay, there are no non-analytic points. The reason is very simple. Well, at least when you do it in perturbation theory, all the integrals in a Wilson action involve, so where's your, so in this integral, for instance, what are you integrating over? You're integrating over a finite range, half to 1. It's a finite range integral, so there's no ultraviolet divergences. Nothing is going to diverge in the ultraviolet as a function of any momenta. Secondly, the denominator always has a high momentum between half and 1. So it's some p squared, where p is between half and 1. And r is supposed to be a small perturbation. So this thing is never 0 for any value of q, because it always has to be between half and 1. So you don't have any infrared divergences, you don't have any ultraviolet divergences, everything is finite. Okay, so you expect analytic answers. And in the original language of Kadanoff, the reason is each step involves only a finite number of degrees of freedom, the iteration. So when you iterate with a finite number of degrees of freedom, you start from one Hamiltonian. The new Hamiltonian is also going to be an analytic function of the old Hamiltonian. The non-analyticity can only come when you have an infinite number of degrees of freedom. Here at every stage, it's only a finite number. So in mathematical terms, these integrals are completely finite as a function of q. So these guys are all analytic functions, and you can expand them about q equals 0. So that's, so u2q, the expansion is this. First term is this, then this. Then you can get a next term. So we'll write down that term. So here's, is there a question? No. So u2, so we'll assume that u2 star q is some r star plus q squared plus, what have I assumed it? This is order epsilon squared, but I think I've assumed a form, yeah. I said let's assume it's this form, v2 star q, where this is order epsilon squared. We've already shown that it can only come at order epsilon squared. Now we have to see whether it's self-consistent diagrammatically. Okay. Okay, so the important point now, this is important. So we've already chosen this normalization. Where is the normalization? This normalization. Remember, this is the normalization of the spins. How do you choose it? You choose it so that this leading term is always q squared. That's how you choose that. So all the q squared is there here. So this starts off as q fourth. Okay, so this starts off as. So that's going to be important. So the first example of what I'm going to call an irrelevant coupling is this. And it's actually a higher derivative. Q fourth means higher derivative than the leading kinetic term, which is 2. This is 4 derivatives. Okay. So what is the recursion relation? So you put this into your recursion relation, leading order. And where is that? So this equation has that V2 in here, in the denominator. So what is our first assumption? We approximated this by putting in the leading term. So this becomes 12. I'll just stop in a minute. Times u star. So this was the leading approximation. Plus corrections. Because the corrections to u4 are higher order, and this correction is also order epsilon squared. So you'll have some order epsilon squared corrections here. Okay. So this correction, so this v2, therefore, you expect it to be of order epsilon squared, and I'll write it as, so we'll assume that v2 star q squared is epsilon squared times some f2 q squared. And we'll try to fix this function f2, or at least show that it converges. So actually you get an equation, so you plug that into this iteration equation. So this is the correction piece, and there's a correction piece on the left-hand side. So your correction is v2 star q is 4 times, what correction comes from that? Remember, this is chosen to be 4. This is not affected leading order. So it's 4 times This is the same rescaling that we always do on the right hand side, plus this correction epsilon squared f2 star q. So this is the fixed point equation you have to solve. Okay? And you can actually solve it very easily, because when you put this as q4th, this is actually 1 by 16 here. So it starts off as 1 by 4. So you can iterate it because of that 1 by 4. And so you can start off by assuming that V2 equals that, put it back in, and you'll get a series. I'll just write that series and stop. So if you put, and you can check that this is what you get. You'll get a series solution which is of this form, epsilon squared sum over n equals 0 to infinity, 2 to the power of 2n, that's from this guy, f2 star 2 to the power of minus n q. Okay? So when n is 0, this is just f2. So that's your leading approximation. When you iterate once, you get f2 plus one more f2 with a smaller q, and so on, an infinite number of q's. And this goes as 1 over q4th, so this is 2 to the power of minus 4n q to the power of 4. And this is 2 to the power of 2n. So this is 2 to the power of 2n, 2 to the power of minus 4n. So it's basically sum over n 2 to the power of minus 2n times q squared. It's of that order. So it's a convergent series. Okay? So you can assume that f2, this assumption that f2 is of, this v2 is of order epsilon squared f2 is a consistent one. Your series sums to a finite answer which you get which you can, I mean, in a self-consistent way, and therefore this assumption is good. And the crucial point is this worked because this started out as q4th, and there's a 1 by, so it ended up with a 1/16th here rather than 4. Okay. So what I've shown is that v2, the correction, is indeed of order epsilon squared. So this is, just take 1 minute to write v2. So v2 q I can write as w1 q4 plus w2 q6 plus w3 q8, expansion like that. Okay. And these are the irrelevant couplings, higher derivative. And you can show that, I'll come back to this, I don't want to do it in a hurry. The w1 prime, you can show that w1 prime is 1 by 4, w1, w2 prime is 1 by 16, w2, and so on. Okay? So I've shown you that it's of order epsilon squared, and it occurs, it doesn't affect this in this equation, it occurs with two powers in the denominator, so it won't affect this equation. But I don't want to go through this in a hurry, so I'll just start from this point next time and just complete the argument about how it doesn't affect these equations. Okay? So we'll stop here. So to summarize, what we've shown is the behavior of the fixed point for the simple model. And what we've almost shown is that if you modify the simple model to include these so-called irrelevant couplings, it doesn't affect your fixed point solution to leading order. The order epsilon, so if epsilon is small, there are going to be small corrections. So your analysis is in some sense self-consistent. Okay, so stop.
These irrelevant couplings appear when we are doing the blocking, right? Not
Yes. Yeah, so in fact, yeah, so this is the term that first generates the irrelevant coupling.
they are not on the first term.
No, they're not there in that. So if I assume, if I do this, not this one, sorry, the equation for u. If I do this calculation, maybe I'll say that again next time. Even if you start with u4 and u4 being just two numbers, the denominator has all the q's in it. So the final expression will have q's, q1s and q2s multiplying it. Okay? So it will be some constant times q1, q2 times sigma 4. So you automatically generate terms of this type. In other words, the vertices acquire a momentum dependence, which is not there here. It's just a constant. That comes from each iteration. Okay, so I'll just wrap this up next time and then